You guys had a good weekend? Good, good. All right, so today is the due date for your first assignment, and I can actually check. I can look at the assignment and I can see for every question what percentage of you guys have completed it. And as of last Friday, I think most questions were like over 80%. So it was good to see most people getting an early jump on most of these questions. The due date is 11 p.m. tonight, and just to make sure you know, you don't actually have to do anything formal to submit your assignment. It just automatically submits whatever you've done by that point in time when 11 o'clock strikes. All right, online people can hear me okay? So we are going to finish off chapter 2 today and hopefully start chapter 3. And what we're going to do first is we're going to take a look. I just want to briefly recap so it's fresh in everyone's mind, the functional groups that we've already discussed. Okay. So we talked about hydrocarbons are compounds with hydrogen and carbon only and nothing else. And so if you have all carbon-carbon single bonds, like this zigzag guy here, it didn't draw very well, but we would call all single bonds alkanes. If there's a double bond in there somewhere, we call it an alkene. And if there's a triple bond in there somewhere, call it an alkyne. And notice the way I drew that. I drew these sort of zigzags for all of the other ones except the carbons around here. Any guesses why I drew it this way? Why I didn't draw it like this? The reason is that this carbon is sp hybridized, both of these carbons. sp means 180-degree bond angles, right? Linear, these all should be 180 degrees. So I just drew it the way it looks. Whereas all these other ones like over here are 109.5. So I'm trying when I'm drawing these zigzag structures to approximate or like get close to correct for what these should actually look like. All right, what else do we have? What other functional groups do we learn? Anyone want to throw one out there? Yeah. Alcohol has an OH on it. Good.
Ketone.
Heard something from the online. Say it again.
Ketone.
Ketone? I think maybe is what I heard. It's not very loud on my speakers. Ketone means you have a carbonyl group, which is a carbon double bond oxygen with a carbon on both sides. That's a ketone. And there's a close relative to a ketone where instead of two carbons, you have a hydrogen on one side. What do we call those? Yeah, those are aldehydes. I'm going to try to turn my speakers up if I can. It's not letting me. Okay. Do we miss anything? Yeah, we missed a whole bunch. What else? Alkyl halide. Good. Alkyl halide would have a halogen on there. Sometimes we just say X, where X can be fluorine, chlorine, bromine, or iodine. Sounds like it should be iodine too. And I guess you could call it iodine if you wanted, but anyway, that's an alkyl halide. Esters, I'm going to zip this up just a little. Ester has a carbonyl group, an oxygen, and then another carbon group. Something like this. Ethers, not to be confused with esters, have It's like an alcohol where you replace the hydrogen with a carbon. Carboxylic acids. Carboxylic acid is kind of like an alcohol where we have a carbonyl group there as well, which makes that really acidic because the anion has resonance structures. We looked at these examples before. What else? A couple more. Amines. A nitrogen attached to a carbon. And then what else? Amide, also not to be confused with amine. Amides have a carbonyl group with a nitrogen attached. Aromatics. Aromatics typically have a 6-carbon ring with alternating single and double bonds. Nitriles. So if you have an R, which is just a carbon group, the C triple bond N. Nitrile. That might be all of them, is it? Yeah. If you can check our old notes, you can see that we've got all of them. Sulfides are other ones that we didn't really talk about, but they have SHs. It's like an alcohol where you replace the sulfur with a sulfur. Replace the oxygen with a sulfur. This sulfide. Okay, so we spent last class introducing and looking at infrared spectroscopy as a way of detecting functional groups in a sample or in a molecule, right? So if you have a sample of some substance, you could run an infrared spectrum and you'll get something that looks kind of like this graph we have on the screen right now. And by looking at the features on that graph, you can sort of make some conclusions about what there might be in there. So we talked last class, we said that there were, as soon as you see one of these, there are 2 wavelengths, or 2 wave numbers, I should say, 2 numbers on the bottom that you should draw a vertical line right away. What were those 2 numbers? 1600 was one, and 3000 was the other. So in this example, we have a 3000 right here, vertical line, and a 16, which is right here. So what do we call all this part of the spectrum over here? Yeah, fingerprint. Where we usually don't get too excited about stuff that's in there. Okay, ethers we said was an exception. If we suspect there's an ether in there around, somewhere in that range, you see a strong peak. What do we find kind of in this part of the spectrum? That's usually where you find double bonds. So like CC or CO. Or CN, you rarely see carbon-nitrogen double bonds. What about this region here? Triple, which would be CC or CN. Nitriles or alkynes. And then everything above here is bonds to hydrogen. So right there is where you find sp3 hybridized carbons bonded to hydrogens. And we say that's a stretching vibration that it's associated with. And on the other side is where you find sp2 CHs. We also said sort of around here you would find sp CHs. If you have a terminal alkyne. Okay. So you guys are going to get really good at this. You're going to be able to see a spectrum. Those of you who are checking out the Instagram, there was a question this weekend where I give you a spectrum and I give you 3 molecules and I say which molecule is consistent with this spectrum. So you look at each molecule, you look at the features, and you look at what you'd expect to see in the spectrum if you had that molecule. And, you know, usually only one of them fits. Well, always only one of them fits. I wouldn't ask you a question with two super similar molecules. So ethers, they don't have any carbon-carbon double bonds, no triple bonds. Really, the only thing going on here is a whole bunch of sp3 CHs. So you see a big band for all those stretches. And you can see this peak over in the fingerprint region, which normally we don't bother with, right? So if you ruled out everything else and you thought there might be an ether, you might go looking for that peak, but you don't start digging in the fingerprint region as your first go. Look at all the other features first. Okay. Alcohols are next. Alcohols are one of the easiest ones to pick out. Alcohols have a bond to hydrogen, an OH, and the OH peaks are typically very strong and very broad. They don't look like all the other peaks we've seen so far. All the other ones are kind of sharp. They might be a little bit broad, but jagged at the bottom. OH is sort of big, wide, strong. And so you can see this OH peak right here. Can't miss it. If you look at your spectrum and you see that in there, right away it's like, okay, there's got to be an OH in this compound. Okay. I guess one caveat to this band is that sometimes you might run a scan of a sample that's wet. Like there might be a little bit of water in it for whatever reason. You didn't dry it out completely or whatever. If there's water in it, water shows up there too, because water has OHs, right? So I won't give you examples that are wet. I'll give you nice, pure, clean molecules when I give you spectra on a test or anything like that. But just to know that if you're in a lab or if you're in the real world applying this and you see a big peak there, it doesn't necessarily, it could also mean other things. It could mean, for example, your sample's wet. So 1-butanol has that big OH peak. Remember, the first thing that we do is we go to 3000, we draw a vertical line, we go to 1600, vertical line. So this is all fingerprint. So we're not going to get too excited about all of that. No double bonds, no triple bonds, so it's all kind of blank in this region. And then you see a big, strong sp3 CH stretch, which is great because all of these carbons on 1-butanol are sp hybridized and they all have hydrogens. So we expect to see that big peak as well. Great. Aldehydes. So aldehydes are the first functional group we're going to look at that has a carbonyl group. Carbonyl groups are maybe the second easiest thing to spot in an infrared spectrum. They give you a very, very strong band, somewhere typically just to the left or a little bit higher than 1700 wave numbers. So we're going to take our 3000 and our 1600. We're going to kind of ignore our fingerprint, and we're going to look and we see a very, very intense, strong, characteristic band right there. You can see based on the number, this would be 1700. It's between 17 and 1800. It's very strong, meaning that band extends all the way to the bottom of the screen. Okay, those strong bands around 1720, 1730, 1740, somewhere around there are carbonyl groups. So aldehydes have carbonyl groups. It's not the only functional group with carbonyl groups though, is it? Ketones have them. Aldehydes, ketones, esters, amides, carboxylic acids, they all have a band like that. That carbon-oxygen double bond. Okay. So you can see that. The other thing that aldehydes have that are unique, it's got a special kind of hydrogen. It's got a hydrogen attached to an sp2 carbon, but it's also got, it's not just an ordinary sp2 hybridized carbon. It's a carbonyl carbon. So that hydrogen that's bonded to the carbonyl carbon gives sort of a unique feature that you only see for aldehydes, and it's called a Fermi doublet. And it gives a peak usually around 27 and 2800 reciprocal centimeters. And you can see it here. It's, I mean, you can see definitely there's one peak there. There's a second peak that's there as well, but it's kind of overlapped by this peak here. So we call that thing the Fermi doublet. It's the only time you ever see anything around 2700. So when you have the right-hand peak of the Fermi doublet, and it's for aldehydes. You see there's no sp2 stretch, which is good because there's no sp2 carbons in here, except for the carbonyl carbon, which gives you the Fermi doublet. See the carbonyl peak. Other than that, you see a whole bunch of sp3CHs. So you're going to find that these sp3CH stretches aren't that diagnostic because most molecules will have them. So you kind of expect almost everything is going to show that thing. But that Fermi doublet is definitely unique for aldehydes. Ketones look exactly the same as aldehydes, except they don't have the Fermi doublet. Right? Ketones have a carbonyl group with carbons on both sides. Because there's no CH over there, the Fermi doublet's gone. And all you see in this case will draw a vertical line at 3000. Everything to the right of that is going to be an sp3CH stretch. And you can see in the molecule it's over here. It's just a whole bunch of sp3 hybridized carbons with a carbonyl, and the carbonyl group is right there. Just a little bit above 1700 and strong all the way to the bottom. This is the most obvious feature in this whole spectrum. 1600 was our other vertical line, so that everything over here was fingerprint, which we're not going to dig into the weeds there. Great. We're doing wonderful. Esters. So esters, you can see this example of a molecule right there is an ester. They have a carbonyl peak as well, which makes sense. They have a carbon double bond oxygen. So between 17 and 1800, CO stretch, STRE, get my spelling right here. Other than that, vertical line at 3000, there's no peaks to the left of that line. By the way, little things like that you can just ignore. There's sometimes little tiny peaks that we call overtones, which are something that you can forget about. This would be an sp3 stretch, CH stretch. The other thing, if you look at the molecule of an ester, it kind of has a carbon-oxygen-carbon part. It looks kind of like an ether with a carbonyl group. And so ethers, remember, had a big strong peak in the fingerprint region. Esters do too. So you can see this peak right there is a carbon-oxygen-carbon. Again, that's not a great one just to rely on, just because it is in the fingerprint part of the spectrum. And given that, it's, you know, there's lots of stuff going on in that part of the spectrum, so it's not super diagnostic. If you have an ester, you should find one there. But if you see something there, I wouldn't immediately conclude it's an ester. Carboxylic acids. Here we go. Third most obvious peak. Most obvious alcohol. Second most obvious carbonyl, CO stretch. Third, carboxylic acids. It's like an alcohol. It gives you a big broad peak on the left-hand side of the spectrum, but maybe this is the most obvious one. It like swamps out like half the spectrum. It's huge. You can't miss that peak. Okay, it obscures everything that's underneath it. 3000, we're used to kind of drawing a vertical line at 3000. This swamps out all the ordinary CH stretches. You can kind of see maybe a little bit at the bottom. Notice that this compound has a phenyl group, which is all sp2 carbons, right? All sp2s with hydrogens. So we expect on the left side of that line for there to be sp2 CH stretching, just above 3000. And we see some, like, you know, some stuff there, but it's sort of buried underneath that great big carboxylic acid peak. Same thing on the other side. There's probably some sp3 CHs, but they're both overwhelmed. They're both basically they're swamped out by that great big OH peak on the carboxylic acid. So carboxylic acids show this gigantic peak that swamps out the left-hand side of the spectrum. Plus, it shows a carbonyl peak because it's got a carbonyl group, and then a bunch of fingerprint stuff. Cool. Nitriles. So nitriles, they have a triple bond, don't they? Here we go. This is exciting. We never see anything in the triple bond part of the spectrum, but right here, somewhere around, say, 2200 wave numbers, which is where triple bonds come, we see this very strong band that goes all the way down to the bottom. CN bonds are strong, they are polar, and so you see this very nice, strong feature there. We don't see too much else. We see sp3ch stretch. We don't see any sp. There's an sp carbon here, isn't there? How come we don't see sp-ch stretches, which would be like out here? It's because that carbon doesn't have any hydrogens attached. You need an sp carbon with a hydrogen to see an sp-ch stretch. Cool. 1600, we would say fingerprint. And no double bond, so nothing in the double bond part of the spectrum as well. Look good? Great. Okay, so what we're going to do, we're kind of done the meat of this chapter, and it might feel like we're whipping through the material very quickly because we've finished two units out of like 9 or so that we're going to finish in the course. We have a third unit coming up as well, which is also very short. I'd say by the time we hit about chapter 5, especially chapter 6, we're going to start spending a lot more time on each unit. There's a lot more, I'd say, conceptually maybe more difficult material later, but we're laying the foundation for all of this now, which is good. Okay, I have a couple of molecules here, and I just want to identify functional groups. Okay, so I'm going to circle one, and I want you guys to just yell out, tell me what it is. And if you're online, you can yell just as well. There we go. Alcohol, that's good. How about that one? Alcohol. What about this? Amide, the D. Amine doesn't have the carbonyl group. And what's this last one on the other end of the molecule? Carboxylic acid, that's good. This molecule down here,
Carboxylic acid.
yeah, that's also a carboxylic acid, even though I didn't draw it out in bond line structure. That's a condensed structural formula for a carboxylic acid, CO2H, or sometimes COOH. You see that as well. So that's the same thing right there. How about this? Amide, aromatic, amine. Now this one gets interesting, doesn't it? This is a naturally occurring compound. I don't know what compound this is anymore. It's a biochemical, like it's an important one, like NADH or one of those. What is that? Nicotine? I don't know. I'm not a biologist, so. But it's got a nitrogen there, which is what? Amine. This has got this group, which is this amide. This one's a bit of a trick if you look closely. It's kind of got a 6-membered ring, 6-atom ring with alternating single and double bonds. So actually, even though they're not all carbons, this is still technically an aromatic ring. All right. How about this one? This one looks exciting, doesn't it? These are real molecules. Plants make very complex molecules like this. But I want you guys to not think about this as like a whole bunch of crap and therefore I can't understand it because it's too complicated. Break it up into little pieces. Just look at the different parts of the molecule and see if there's anything that you can recognize. So yeah, there's all kinds of things here that we recognize, different functional groups on this molecule. I think this molecule might be Taxol. Just looking at the structure. Taxol is an anti-cancer drug that is extracted from the yew tree. And it was first found in the Pacific yew, and they found it in the bark. So the problem was you had to strip all the bark off the tree and kind of extract it like tea out of the bark, and it would fight cancer quite well. But to treat one person, one course of Taxol required cutting down something like 20 acres of this tree. And the tree took, I don't know, 20, 30 years to grow. So chemists tried to synthesize this compound. It's very complex, and eventually a chemist named Casey Nicolau and his group eventually got it figured out. Problem was his percent yield, it took like 60 steps, and the percent yield was like 0.01%. So it was actually cheaper to get it from the tree. But they've since found a way to make it using a European yew tree that makes a similar molecule in the needles. And the needles continuously fall, and they don't kill the tree to collect the needles. And then like 2 or 3 chemical steps would convert it into the active Taxol that you see here. But this is just full of functional groups. So what do we have? We've got 2 of these guys, 3 of them. Those are aromatic rings, they're aromatic. We have this amide, alcohol, ester, alcohol, another ester, another ester. That one's an ether. Ketone, yeah. Carbons on both sides, here and here. How about this? Alkene. Ester. Good. I think we didn't miss anything. Here's one. IR spectrum. Tell me which compound A, B, C, D, E matches this spectrum. So first thing we're going to do, vertical line at 3000, vertical line 1600. So we have our double bond region, triple, double, fingerprint, and this is bonds to H. We got B here's what people are guessing. I would agree with that. What do we see? We see an OH stretch. We see sp2ch right there, just to the left of that 3000 vertical line. We have sp2 carbons on this molecule. We have sp3s, ch, and over here we have a carbon-carbon. How do we know that's not a carbon-oxygen double bond? Carbon-oxygen double bond comes above 1700. So 1700 is right here. So this is between 16 and 17, so it's a little bit too high. Also, it's not that strong. It's like it goes down maybe like past halfway, but it's kind of skinny, sharp. The carbonyl group's kind of broader, big, strong thing that goes right to the bottom, typically. So that's correct. B is the right one. Another example. Again, we're going to go to 3000. Vertical line. 1600, right? I think we said. A good way to start these, I often find, is to start eliminating choices. If there's anything you can kind of eliminate right away. So the first thing I always look for, is there a big OH peak? No, there's not. So the alcohol's gone. Is there a big carboxylic acid that swamps out the left-hand side of the spectrum? It's not that either, so we can probably get rid of the carboxylic acid. We're kind of down to these three, B, C, D. B and C are aldehydes, and D is an ester. So I'm saying it's not D. Why is it not D? Yeah, there's nothing in the fingerprint region around 1,000 or 1,200, 11 that you'd expect. So it's kind of like nothing strong out here, which suggests it's probably not an ester. Is there any other pieces of information that suggests it's not D or that it must be B or C? People are saying C. Why? What else do you see? What's that? Can't hear you.
Double bond? The double bond?
Tell you, yeah. So what we can see, CO, CC. So we have two double bonds here, carbon oxygen and a carbon carbon, which matches C but not B. Is there sp2ch stretches? Well, I don't know. A little something there, but not much. So sometimes it's not as well behaved as all of the examples that I give. Okay, so I would say that's definitely a carbon-carbon double bond. It kind of peaks out, it's in the right spot, it looks right, it's in the right area. I would say there's definitely a carbon-carbon double bond here, which would make me pick C over B, even though maybe it's hard to see the sp-CH stretches, sp2-CH stretches. What else do aldehydes have that are diagnostic? Yeah. Fermi doublet, yeah. Fermi doublet. Fermi doublet right there. Great. Another example. This is the IR spectrum for aspartame. The molecule structure is right there. You guys know what aspartame is? An artificial sweetener. It's got a lot of stuff going on in it, doesn't it? It's got an ester right here. It's got an aromatic ring. It's got an amide. It's got an amine, and it's got a carboxylic acid. What do we see on the left-hand side of the spectrum? A big, ugly, giant peak right there. What else do we see? This is 1600, which is normally where we draw a vertical line. So basically what you see is some peaks in here. The question is saying, what peaks are characteristic of the carboxylic acid group? In fact, you could answer this question without even seeing the spectrum. The broad peak extending from 38 to 22 and the strong peak at 1720. The broad peak extending from 17 to 1000 and the strong peak at 720. Strong sharp peak at 700, which I guess is that guy. It's not that one. The peaks between 3000 and 2900, no, that's sp3ch stretching. And the large broad peak between 3000 and 1700. Well, I'd go with A for that one, because carboxylic acids have two features. That big broad thing right here and the carbonyl group. Okay. Which of the following compounds is consistent with the following IR spectrum? So there's 5 molecules on the right. The axis is a little harder to see here, but we have 3000 is right here. This is 2000. This is, can't even see that very clearly. I think this is 1600 right here. I think that is 1500. And I think that is 2000. That's 3000. Oh, it's on the bottom here. I was trying to read those little tiny little letters, but no, the scale is a little more clear there. Okay, what do we see? An OH, good. Is it a carboxylic acid OH or an alcohol OH? Alcohol OH. So let's cross off everything here that doesn't have an alcohol. It's not a carboxylic acid. It's not that. So it could be A, B, or E. What else do you see? Any double bonds? Looks like a triple bond, doesn't it? So B is probably out. No triple bond there. E has a double bond. We don't really see anything where we expect to see a double bond. But that one has a carbon-nitrogen triple bond right there. So that's probably it, A. Right? And then the rest of the spectrum makes sense. We see sp3ch stretching. It's good. Oh, that guy. It's fingerprint, so we shouldn't get too excited, but big, strong peak. Turns out alcohols can sometimes show the same peak that ethers show down there. It's related to carbon-oxygen single bonds. So because ethers and esters and alcohols all have that, sometimes you see a big, strong peak down there. But I wouldn't call that diagnostic either. This is the one that's diagnostic for alcohols. More examples. 5 molecules in an infrared spectrum. 3000, we're going to go vertical here. 1600, we're going to go vertical again. And what do we see for A? See an alcohol again, OH, stretch. What's that? That's right, sp3ch, stretch. What's this? Carbonyl, stretch. And then fingerprint. So which molecule down there has all those features? We got E, do we? B? B, yes. Not E, because E has no OH. It's not A, because A has no OH. A would also have a triple bond, which we don't see. C is out because it has no carbonyl group. D is out because it has no carbonyl group. So we're going to go with B. So it's identifying the features, knowing what functional groups or what kind of stretches they go with, and then picking the molecule that has all the right features to match it. Okay. So that's it for that unit. What I'd like to do is introduce the next unit, and the next unit is quick, pretty quick. It's on acids and bases and mechanisms, and acids and bases are something that you guys have seen, like probably you started in, I don't know, grade 11, and you do acids and bases all the time. And we're going to do acids and bases again, but from a slightly different lens from what you're probably used to doing. Usually when you've done acids and bases before, you're probably thinking of aqueous solutions of acids and bases. Often in organic chemistry, we're not in water, so we don't really think too much Sometimes we are, so we have to remember what we learned in first year. But you probably remember acids and bases, and you're thinking in your head, it's like, okay, I remember weak acids partly dissociate. You do an ice calculation, you can figure out the pH. Then there's titrations, and there's buffers, and there's all this kind of stuff. We're not going to do any calculations with acids and bases. Everything's going to be kind of qualitative, descriptive. And what I want is for people to have an intuitive understanding of acids and bases, as opposed to being able, like, yeah, okay, if I give you a weak acid and a Ka, sure, in first year, I would expect you to go through all the calculations with the ice, do that little approximation, calculate the pH of the solution and all that. That's not what we're doing here. I want you to look at a molecule, pick out the parts of the molecule that are acidic or basic, and what that will mean for how that molecule behaves. This is crucially important for anyone going on to take biochem, because most molecules that are of biological interest have acid or basic groups that will, you put them in water, put them in a cell, put them in an enzyme, will have acid-base chemistry, which is critical for how they behave. Okay. We'll look at some examples. We have a number of definitions of acids and bases that you may remember from first year. First one was the Arrhenius definition, which was based on whether the compound had, I think, H plus or OH in its formula. The Bronsted-Lowry kind of supplanted the Arrhenius definition. And normally in organic chemistry, when we say acids and bases, this is what we're talking about, is the Bronsted-Lowry definition. And in this definition, an acid is something that donates H plus to something else, and a base is something that accepts H plus from an acid. So in a classic example where you add HCl to water, HCl is the acid because it donates an H plus to a molecule of water. Water is a Bronsted-Lowry base because it accepts the H plus and becomes H3O plus, becomes hydronium ion. It's a very classic acid-base reaction. But you don't need water. It can be other things that are acting as a Bronsted-Lowry base. I have an example here of acid. It's acetic acid. It's an organic acid. It's a carboxylic acid, isn't it? Right? And it's reacting with a base, in this case also an organic base. This is an amine, triethylamine, we call this guy, tea. But it's not the kind of tea you want to drink. In this example, what happens is the acid can donate a proton to the base, and that becomes acetate. So you get the anion, which is the conjugate base, and you get it's called a ammonium cation. An amine becomes an ammonium, and that would be the conjugate acid. So this is just a Bronsted-Lowry acid-base reaction that doesn't involve water at all. And that's kind of important in organic chemistry because in the lab we often don't use water. And it's why we don't like the Arrhenius definition, because that is strictly limited to situations where you're dissolving things in water. So we like to use the Bronsted-Lowry definition. Curly arrows, I think I introduced this before when we did resonance structures. We use curly arrows to track the movement of electrons. So if you are doing a resonance structure, like let's pick an example off this slide. Okay, this is a resonance form of the carboxylate anion, the conjugate base here. We could use resonance structures to show you you can use curly arrows to show how the electrons move going from the left structure to the right structure. There are some curly arrows in the assignment this week, right? Yeah, we're going to use these again. Curved arrows are sometimes called too. So that shows that electron pair going down, and that makes a double bond leaving only 2 pairs of electrons on the oxygen. At the same time, we're going to put a pair of electrons back up on the oxygen. So that shows you how you convert the left structure to the right structure. To go back, we would just do something like that. Now, up above, what we have is a chemical reaction. Bonds are breaking, atoms are moving, new bonds are forming. This is not a resonance structure, this is a reaction. And we use these curly arrows for reactions as well as resonance structures. In fact, that's the main use, I would say. Because sometimes you see an organic reaction where you have a starting compound or starting compounds, and then all of a sudden you have products, and you look at it and you have like, I have no idea how this went into that, how those bonds broke and became this thing all of a sudden. But if you draw the curved arrows, what that does is it shows you exactly how the electrons move, how you got there, right? It's the path that the molecule took to react to give you the product that it gave. So in this example, we can draw in curved arrows that look like this. These blue arrows that you see on the screen now. And what that means, that first blue arrow right here, it means that nitrogen lone pair it moved to the hydrogen, meaning we're forming a nitrogen-hydrogen bond. We're taking that nitrogen lone pair and turning it into a bond between the nitrogen and the hydrogen. I kind of think of it a little bit like, the nitrogen is like a frog, and the pair of electrons is like his tongue. And the hydrogen's like a fly, and it like goes zips out, grabs it, and zips back. That's not how it happens. Electrons don't fly out and gather things and pull them back in. But the way I'm drawing it, it's kind of like it's going to the hydrogen, it's forming a bond, and you have a new bond there. At the same time, that OH bond must break. The electrons in that OH bond move on to the oxygen. The oxygen at the beginning had 2 lone pairs. At the end, it has 3. To draw the lone pairs in. So this reaction, we're showing what happened in the reaction, how the electrons moved using these curved arrows. Okay. So we use these a lot in acid-base reactions. We're going to use them all the time when we get into more complex reactions a little bit later on. There we go. So we use them for resonance structures, and we use them for reactions like acid-base. Nothing special about an acid-base reaction. We're going to talk a lot about acid strength, but we are at 9:20 right now. So I don't want to kind of just start this and quit. So we will resume this chapter at this point on Wednesday. And yeah, I have office hours starting in about 10 minutes too, if anyone wants to jump on.